Before we start, I would just like to mention that the talk is going to be recorded. I mean, it's been already recorded. If anybody has an objection, then please let us know. Otherwise, we proceed. Okay, so good, then perfect. All right, then let me introduce our today's speaker, Mahmoud Khaled from University of TU Munich, Technical University of Munich. Well, Mahmoud is a senior PhD student in our group based in TU Munich, and well, he started his PhD in 2015. And well, before that, Mahmoud was with the University of Minya, where he got his master and bachelor degrees in 2014 and 2009. Well, Mahmoud has received a DAAD PhD scholarship for his PhD in 2015, and more recently, he has received the Best Demo Award from HSCC 2020. Well, his research interests mainly focus on the interplay, let's say, intersection between formal methods from computer science and control theory, in particular on formal verification of safety-critical cyber-physical systems, and also development of software tools in this area, where he has developed quite a few quite useful software tools. And here I can recall a few of them, such as Sense, P-Faces, iExplore, and PIRC, among others. All right, and in this regard, actually, he's going to talk about in his talk on, well, so-called end-to-end approach for automated synthesis of embedded control systems. All right, so then without any further ado, let's welcome Mahmoud to our today's seminar and give full attention to him. Mahmoud, over to you.
Yeah, thanks Naveed for the introduction. And yeah, hello everyone, and thanks for taking the time to attend this talk. This talk will be about automated synthesis of certifiable controllers for cyber physical systems. We will try to introduce an end-to-end approach for automatically designing controllers for cyber physical systems. We start with cyber physical systems. Cyber physical systems are simply collections of computation devices that interact with or control physical systems. Examples of cyber physical systems are airplanes, smart grids, surgical robots. Safety critical cyber physical system is a subclass of cyber physical system where failure or malfunction may result in death or injury to people. Death or injury to people, damage to equipment or property, or environmental harm. Ensuring the correctness of safety critical cyber physical system is then very crucial. The safety critical control software is the brain of safety critical cyber physical system. It interfaces, performs control and planning tasks, and finally commands the actuators. No matter what the size of software is, from simple embedded code to complex software can be considered safety critical control software if it's really safety related. Examples of life-critical safety critical control software are the software inside insulin pumps or fly-by-wire software in airplanes. One common observation here is that safety critical control software gets more complex in order to make our lives easier. Safety critical software is no special case. There is actually a law of conservation of complexity similar to that one for math. It states that every application has an inherent amount of complexity that cannot be removed or hidden. Instead, it must be dealt with either in product development or in user interaction. As safety critical control software becomes more simple to use, more user-friendly, and more complex, there is a high possibility of faults and consequently more fatalities and injuries. And finally, less trust from the community. We all know how modern, easy to drive, and most importantly, autonomous Tesla cars are. But let's not forget that last year in Taiwan, a Tesla car crashed into an overturned truck as its autopilot failed to recognize it. Imagine how happy the pilots of your plane are when they know that their plane is equipped with a cutting-edge autopilot. But let us also not forget that in 2019, the faulty maneuvering characteristic augmentation systems, in short MCAS, in Boeing 737 MAX crashed and caused the death of around 350 passengers in 2 consecutive crashes. So far, I tried to motivate you and possibly convince you that safety critical control software is getting complex. And as a result, more faults happen and we pay higher costs. You may be also convinced that the correctness of safety critical control software is not tolerable and it needs more attention. The question is, why do things go wrong with safety critical control software? In short, we do mistakes. Here is a diagram of the development cycle of safety critical control software. Such waterfall model, although not exactly what used nowadays in industry, but has the parts that we need to pay attention to. It starts with requirements collection, where the design requirements of the software are collected and analyzed. Imagine that Mr. SpongeBob here is responsible for it. Funny, yeah? Everyone likes SpongeBob. He is, however, naive and very optimistic. As a result, we get requirements that are false or ambiguous. He may also miscommunicate them to other people responsible for the next steps. Next step is design and development, where the actual software is designed and coded. What if Alice here is responsible for it? You know Alice from Wonderland, Alice in Wonderland. Yeah? Everyone likes Alice too. Unfortunately, Alice does mistakes and writes buggy code. Some of them are logical issues that are hard to find. Anyway, Alex was not ready for Wonderland when she fell into that rabbit hole. Similarly, we are not ready for safety critical control software and insist on using all the design and development approaches. Next step is testing. We assign testing to Eve. Not everyone knows Eve. She is an important character in most cryptography classes. She tries to decrypt the message between Bob and Alice. Here, she tries to find bugs, a similar annoying task. She is, however, human and does mistakes. She can't cover all testing possibilities, and consequently, many edge cases are left undetected. Now, deployment. This time, let's give it to the best of us. Otherwise, the software will definitely fail. We give it to Einstein. Oh no, he's good only in math. Let's try someone who's good in practical stuff. Let's give it to Nikola Tesla. Again, Nikola is a human and makes a mistake. He should have paid more attention to his lab. If you recall, Tesla's lab went on fire on March 1895. All of his inventions, model plans, notes, lab data, and photos were destroyed. Sorry, Nikola. Finally, one more testing phase. For sure, this goes to Eve. Testing is annoying anywhere. So yeah, disappointing. If we humans do mistakes and not fit for safety critical control system design, who is? Well, we will see. Let us brainstorm together how to improve such software development cycle. We need to eliminate or reduce the sources of faults. We need less testing through development steps that produce software we can trust. We may automate the design and development tasks, giving no chance to human-related bugs. We need to find new ways for specifying the specification in more precise, formal, and unambiguous way so that we can safely communicate them. We need to have certifiable software control system deployments. How can we achieve all of this? Well, there is a promising group of approaches called formal methods in control. They provide automated synthesis of certifiable safety critical control software. The software is guaranteed to satisfy the requirements, and the post-development testing may not be required. They can also handle complex high-level specification. An example of formal methods in control is symbolic control, which we will discuss in detail later. Now, we are done with the motivation of this talk. We have symbolic control as a candid, promising approach for the design of safety critical control software. In the next part, I will give an overview about symbolic control and why it's not yet used in safety critical control software if it is that promising. In a nutshell, symbolic control is an approach for automated synthesis of controllers for control systems. We start with a dynamical system described by some mathematical model. As the state of the model have infinite values, we cannot work with them algorithmically. Instead, an abstraction is constructed from the model. This comes in form of finite state system that we refer to as the symbolic model. A formal relation between the original system and symbolic model ensures that the controller synthesized for the symbolic model can be refined to work with the original system. The synthesized controller is referred to as symbolic controller. Once refined, it ensures that the given specifications are enforced on original system. We discuss it more formally next. We start with control systems. A control system is sigma is a tuple x, u, f, where x is a set of states as real vectors. U is an input set as real vectors. F is a continuous map satisfying some general Lipschitz assumption. A trajectory of sigma is defined by the locally absolutely continuous curve z if there exists a continuous curve nu that satisfies this ODE. On the other hand, a system is a tuple x, x0, u, t, where x is a set of states, possibly finite. Xu is initial set, u is an input set that's also possibly finite. T is a transition relation. We say that S is symbolic if x and u are both finite sets. For an x, we use ux to refer to the inputs admissible to x. A sampled version of sigma called S tau is a system x tau, u tau, t tau, which encapsulates the behavior of sigma at sampling times k tau. You may think of it as a control system surrounded by a sampler and a zero-order Hort. We use this simplified version of systems with 3 sets when the initial set equals the state set. In S tau, a transition of S tau is the tuple starting state, a piecewise curve of input applied to sigma, and the final state reached after tau seconds. Please notice that x tau and u tau are uncountable, and hence S tau is not symbolic. We still can't work with it algorithmically. We introduce feedback refinement relations as means of relating control systems and symbolic models. Let Si be 2 systems such that U2 is subset of U1. A strict relation Q is a feedback refinement relation if the following hold for all pairs x1, x2 in it. The inputs admissible to x2 are also admissible to x1, and if U is admissible to x2, applying it to x1 in S1 and mapping the post state through Q results in post states of S2 if the same input is applied to x2 in S2. Q is used to relate system S tau with its symbolic model. Here S tau is S1 and the symbolic model is S2. The symbolic model is system SQ where XQ is a cover or a partition of X tau and UQ is a finite subset of U tau. TQ is designed such that there exists a feedback refinement relation from S tau to SQ. Clearly, designing a symbolic model here boils down to designing TQ. So how TQ is designed? We start with an example trajectory of sigma with some initial state x0 input and the final state. XQ in SQ is chosen as a partition of X tau. The initial state lies in subset XQ, and we want to compute those transitions starting from. Since XQ is a set, we need to use approaches from reachability analysis to compute the reachable set under F. We approximate the reachable set with 2 vectors, X lower bound and X upper bound, enclosing the actual reach set. Map omega here is used to refer to such over approximation. A final approximation is to identify the symbolic state that touch the reach set. We use map OF here to refer to this operation, which in this case is done by applying the output of omega F to the feedback refinement relation Q used as a map. We now know the transitions, and we repeat this process for each initial state and input. Although simple, this process is computationally complex. This algorithm shows a traditional implementation of the construction of TQ. See the nested for loops and how they increase the computational complexity. Note that set XQ and UQ are vectors of sizes n and m dimensions. This is how the process happens by repeatedly computing the parts in TQ. A simple complexity analysis will lead us to the concept that is known as the curse of dimensionality. If the number of samples in XQ is exponentially related to some constant in X, representing a uniform quantization over state dimensions, we have an algorithm with exponential complexity in the dimensionality of the original system. One observation that will help us later is that the computation for each pair XU is independent and can be done in parallel. Now, having a symbolic model, we design its symbolic controller. Symbolic models can be equivalently seen as label-directed graphs. Each partition element is a node in the graph, and the transitions are the edges, labeled with inputs. We do some operations on the graph. We defined a predecessor computation map, C pre, that takes as inputs set Z as pairs XU that and computes those pairs that reach in one step the states of Z. The synthesis starts with a formally defined specification. Here we consider a simple reachability specification given by the LTL formula reach psi. From psi, which is a logic propositional formula, we can compute an initial winning set of pairs using some mapping function L. We also define a monotone function GZ that utilizes the C-pre and the initial winning set. We finally extract, sorry. We now solve the so-called minimal fixed point by repeatedly computing GZ until no more results are obtained. At this point, we say the fixed point has settled. We finally extract the controller as a map that provides for each state a set of candidate inputs that can be applied to enforce the given specification. Three important observations are necessary here. One, complexity of synthesis depends on the supported specification, and synthesis suffers too from the curse of dimensionality. Two, using mu calculus here is hard and tedious, since different fixed point schemes will be needed for different specifications. This is why all existing symbolic control tools are limited to simple specifications. Finally, there is no standard approach of collecting the controllers, which leaves the task to ad hoc implementations. The question is then, is it practical to use symbolic control as it is? A simple answer, no. The specifications are formal, but still naive and not practical. Due to the curse of dimensionality problem, the design and development phase may take long time and may not finish, which limit the symbolic control to small-sided systems with less curse of dimensionality symptoms. The deployments are ad hoc and ruin the formality and guarantee obtained from the previous steps. Symbolic control can be improved in 3 steps. Step 1, we use scalable algorithms for abstraction synthesis to mitigate the effects of the curse of dimensionality. Step 2, support richer specification and unify the synthesis process. And finally, provide a standard formal approach to controller abstraction and generation. These will be our jobs till the end of the talk. In the next slide, we will provide efficiency enhancements to symbolic control. I will take first a short detour to introduce a framework that unify and simplify the design and implementation of those efficiency enhancements. So far, we know that safety critical control software needs a practical formal approach. And we know that symbolic control is not ready for real world applications due to the curse of dimensionality problem. On the other hand, we are now living in the age of high performance computing devices. They have millions of processing elements and virtually unlimited memory. They are everywhere, from local gaming PCs to supercomputers. They are diverse. CPUs, GPUs, and hardware accelerators can form high-performance computing devices. They are available and accessible. They are used in many applications like simulation and many computational branches of science and engineering. So why not utilize them for symbolic control? 2 years ago, we introduced P-Faces, an acceleration ecosystem for the design and deployments of formal method in control. I gave a small overview about it as we refer to it in the next part of the talk. P-Faces supports all computing platforms, GPUs, CPUs, hardware, accelerators, and interconnections of them. It has a diverse set of formal method libraries for symbolic set manipulation, parsing, libraries for accessing and generating commonly used data structures like binary decision diagrams and sparse matrices. It also supports code generation, which would make it handy for deployment. P-Faces is kernel-based framework. This means that developers implement their logic as kernels that run on top of P-Faces. This modular design allows for maximum extensibility. The kernel itself is 3 parts: parallel code written in OpenCL, a C-like language, the workflow of the kernel provided as instruction sheets, and the configuration file template used by the users to supply the data input. Once the kernel is designed, one can simply pass it to P-Faces and run it using simple commands. If you are working in a similar domain, or you just need to accelerate your algorithms, I suggest you give P-Faces a try. It's free to use, and there is a demo version that allows you access to around 50 processing elements. We have multiple example kernels that uses P-Faces, which you can use as a guide. So far, we have identified 3 major issues in symbolic control and reviewed our acceleration ecosystem P-Faces. We start by providing efficiency enhancements to the algorithms of abstraction and synthesis. Let us recall the serial traditional algorithm for constructing TQ. Remember how it suffers from the curse of dimensionality issue. We want to find a way to mitigate these effects of curse of dimensionality by parallelization. Let's identify the issues here. First, the two for loops combined run independent computation over pairs in XU domain. Additionally, map OF possesses a special overhead as it internally computes the or computes the quantization that explodes with the dimensionality. To solve the first issue, we parallelize over XU and utilize the sparsity structure in sigma to avoid unnecessary iteration. I discuss with details sparsity in a next slide. To solve the second issue, for now, we can delay to the synthesis phase and do it on the fly only when needed. So the first step is to parallelize the algorithm for constructing TQ. I will just highlight the important parts in the algorithm. So in the parallel algorithm, we have parallel for loop that replaces the nested ones. We have one thread for each pair XU. In short, we have ideal data parallelism. We use map omega f instead of map OF. It's much more compute and memory efficient. Omega f returns two corners, the upper and lower bound of the rich set, whereas OF used to quantize the rich set. Also, instead of having TQ as transitions, we have K as hypertransition. A tuple in K has start state, input, and the bounds of the rich set. TQ can be recovered directly from K when needed by quantizing the rich set. The algorithm simply divides the burdens of computation using P processing elements. Hence, we have P dividing the complexity. The elegancy here is that if P is variable, the complexity changes. P is a variable here means that the ability to add or remove processing elements. Keep in mind that in simple GPU, we have around 2,000 processing elements. Supercomputers have millions to billions of processing elements. Now, in a second step, we utilize the sparsity of dynamics to eliminate unnecessary iterations. The sparsity is a concept in discrete time systems. We build directed graphs of vertices representing variables of inputs, states, and updated states, while edges represent which states or variables affect updated state variables. The more dense the graph, the less sparse it is. We also introduce two sparsity-aware maps, PI and DI. PI is the projection map that works with both states and input sets. Given a set of states of inputs, PI uses the sparsity graph to identify the relation between variables and returns its projection on those subdimensions affecting the updated state xi. DI provides a recovery of the projected subsets. Given a projected subset, DI recovers subsets in the state input space that would produce the projected set. For example, consider a system sigma described by the sparsity graph at the left. Here, state variable x1 affects x1 plus, and x2 affects x2 plus. Now consider subset Z of two-dimensional in set X. A projection P1 generates this subset on x1. The recovery of the projected subset gives us this recovered subset in light orange. Notice that the recovered set is an over-approximation of the original one. Sparsity awareness can be used to reduce the number of iterations in the construction of symbolic model. The algorithm on the left utilizes the sparsity knowledge stored in the graph through the projection maps to only construct abstractions based on sub-dimensions that really affect the updated states. Different sets are constructed, each corresponding to one updated state variable by calling the traditional algorithm for constructing TQ, but on the subdimensions obtained from the projection. Then they are combined after being recovered. We get the same transition relation TQ, but with less effort. Next update is to simply parallelize this algorithm, but so that it scales. Same concepts discussed before are applied, and we have an algorithm that stores the transitions in K sets instead of T to even save time and memory. Algorithm 5 reduces the complexity to the maximum size of the projected subsets. Algorithm 6, although it does the same to the complexity, it additionally adds the ability to control the complexity using different processing elements. A simple example here would give us more intuition about the differences between algorithms. Consider a traffic network described by a long road of intersections. Each intersection adds 3 more state variables to the system. The main feature in the sparsity graph of this system is that as the number of intersections increases, the maximum number of affecting states or inputs is fixed. Actually, we have here a maximum of 3 states affecting each intersection. The graph on the right shows a comparison between the serial implementation in red, the sparsity-aware one in blue, and the parallel sparsity-aware implementation in black. Clearly, the serial implementation explodes very fast. In the second one, although utilizes the sparsity, it tends to explode because of the step in the algorithm that combines all sub-abstraction into one. The parallel one, on the other hand, and because of the distributed data containers, those K subsets, and that we need not to combine them, make the algorithm scales linearly. The concepts of parallelization can be applied to the synthesis as well. To save your time, I summarized the improvements that can be made to the synthesis in 3 figures. The first figure here shows a traditional synthesis approach using fixed point as discussed earlier. The problem here is that the computation of the predecessor map is complex. For each iteration, we need to search the whole state input space for those pairs that will belong to the updated winning set. This search is independent. By simply parallelizing this search, we allow the algorithm to control its complexity. Here, the initial set is shown in green, and its predecessor, the one we are looking for, is shown in purple. Unfortunately, we are here wasting our valuable computing resources by making them do the search in regions of the state input set that we are sure will not belong to the updated set. This is mainly because they are far away from being included in one step. Here we can utilize the sparsity of the dynamics. At any point of time, you have one set and you want to compute its predecessor. We use the projection map to identify which subdimensions can help us gain information about the region. We then apply map GZ that computes the predecessor set, but on the subdimensions. We do this for each projected subdimension. We then recover all dimensional predecessors and compute their intersections. The intersection is an over-approximation of the set we are originally interested to find. Now, instead of doing the parallel search on the whole state input space, we focus our search on regions where less computing resources are wasted. Here comes the question, does all of these improvements make a difference? Simple answer, yes. Let me show you with an example. At the right is the dynamics of a 3-dimensional vehicle used for benchmarking in almost all symbolic control tools. The goal is to reach some target and avoid a maze-like obstacle. We combined all the approaches introduced earlier and tried to solve the problem. We repeated the results reported in all state-of-the-art tools and ran our implementation on the same machine. The results are orders of magnitude in improvements. We took the example to a next level and tried to solve it with more processing elements. While current state-of-the-art tool Scott solved the problem in minutes, we managed to solve it in milliseconds by increasing the number of processing elements. See how the numbers in blue in the table change by adding more processing elements. Since it's here only fractions of seconds, we targeted a more realistic implementation. A car driving on a highway, avoiding a crash, and autonomously doing lane changes. The simulation is connected to Amazon Cloud, where new controllers are solved every sampling period. And the set of control actions are sent back to the car that takes care of applying them and identifying other cars as obstacles to be reported to the cloud. Additional extensions are applied to support stochastic systems with noise and disturbances. Here, symbolic models are Markov decision processes, and the controller synthesis is done with dynamic programming to find optimal solutions. We introduced Amethyst, a tool for parallel computation of MDBs as symbolic models and synthesizing their controllers. Built on top of P-faces, Amethyst provides scalable algorithms for stochastic systems, parallel construction of MDPs, and parallel solution to Bellman equation. It supports wide range of probability distributions and handles complex systems. It's open source and available online. We also made some extensions to improve the computation of our beloved map Omega F. Its computation affects practically the construction of symbolic models, and it can be used independently for reachability analysis. We introduced PERC, a tool for practical interval reachability analysis. Built on top of P phases, it provides parallel ODE solvers, parallel growth or contraction bound computation, parallel mixed monotonicity methods, and parallel Monte Carlo simulations. It can handle billions of dimensions in minutes. It's also open source and available online. Now, we extend symbolic control to support more practical formal specifications. Reactive synthesis is a popular topic in computer science in the last decade. It addresses the following problem. Given some formal specification of systems, can we design the system algorithmically? The system description or specification is given in a formal language like LTL or a part of it. The specification usually describes the input-output relations of system. They are translated into automata. They are translated into automata, and the automata are used to construct games. Then games are solved of them so that we can find a strategy to solve the game. This strategy is translated to machines, and those machines are the implementation of systems. For example, if you need to design a two-sided arbiter, we describe it with an LTL that formally describes how the requests and the grants are handled correctly. Reactive synthesis tools takes care of this and automatically produces an implementation of the arbiter without human interaction. There are fundamental differences between symbolic control tools and reactive synthesis tools. Symbolic control tools handle control systems and synthesize their feedback controllers. Reactive synthesis tools handle finite state systems and produce their implementations. We made a small survey of available state-of-the-art tools from each side, and reactive synthesis tools are much superior in the types of specification they support and the ability to auto-generate the implementations. Next, we will try to benefit from the ideas in reactive synthesis to improve the types of specifications symbolic control can support and allow for a unified representation of controllers. Let us first introduce some stuff. Consider sample time system S tau. Let Px and Pu be sets of atomic propositions labeling subsets in X tau and U tau, respectively, such that Px intersect Pu is empty. A specification for S tau is the subset of all omega words of P, where P is the power set of the union between Px and Pu. The figure at the right shows an example of Px. Px comes with a labeling map that takes the states of X tau to subsets of Px. Similar example can be made for Pu and a labeling function of it. Now, giving an initial set of states x0, a sequence of inputs u tilde, and a resulting sequence of states x tilde, S tau is set to satisfy specification psi if the following holds. For any initial state, there exists an omega word alpha in psi, such that for all time instances, the union between mapped states and mapped inputs should be in the current subset in the word alpha. The figure at the right bottom visualizes this condition. Asking users to provide their requirements in omega words is not practical. Instead, LTL or deterministic parity automata are used. DPAs are more expressive, and any LTL can be represented with some DPA. A DPA is a tuple Q, Q0, gamma, TA, X, D, P, where Q is a set of states, Q0 is an initial state, gamma is an alphabet, TA is a transition map, X is a transition coloring map, D is a maximal color, and P is the parity defining which runs of A are accepted. A run mu is accepted or is accepting if and the only if the highest value that occurs infinitely often in the sequence of colored transitions is even or odd, depending on P. Given system S tau and DPAA such that gamma equal P and psi is the language of A, a controller synthesis problem is asking to find a controller C such that S tau satisfies psi when the applied input sequence U tilde is coming from the controller. Now, starting with sigma and its sampled version S tau, we construct a symbolic model SQ as usual. On the other side, specification psi is represented as DPAA. Having two finite state system SQ and A, we can combine them in a special way to construct a parity game P. Solving the parity game will give us the controller that enforces psi on sigma, the feedback controller. You might be wondering now, what is the parity game? It's a two-player game played between SQ and C here in this setting. It's represented by the tuple VS, VC, V0, ES, EC, and K, where VS is the set of nodes SQ plays from. VC is the set of nodes controller C plays from. V0 is an initial node of the game. ES is the edges played by SQ, and EC are the edges played by C, and K is the coloring map for the edges EC. We developed an algorithm for constructing P from S and A, SQ and A. It simply constructs P by exploring SQ and A simultaneously. I will skip the details of this algorithm to save some time. However, all details about this algorithm will be available in our accepted paper in this year's HSCC conference. We implemented the extended version of the symbolic control in a tool that we call Omega Threads. It supports Omega regular specification and hybrid systems. Inputs to Omega Threads are simple text files. Users usually specify the specification as text LTL formula or DPA files. Built on top of PFS provides a parallel implementation of the approaches discussed earlier. The parallel construction of SQ, the parallel construction of the parity game, and a parallel parity game solver. Controllers are generated as Mealy machines in Omega Threads, and it supports code generation. It's an open source and available online. Let me show you with an example what Omega Threads can do. Consider the following drone model. The drone operates on a battery and is described by a nonlinear impulsive system. Variables x1 and x2 are used to represent its lateral dynamics as continuous time system. The impulsive part represents the discrete time effect of the battery charging and discharging. The battery level is encoded in state x3. The control objective here is provided as LTL formula shown on the right side. In a simple language, this asks that the drone performs infinitely often two different pickup and delivery tasks, pickup 1 and 2 and delivery 1 and 2. When a delivery task starts, it should be completed without starting another delivery task. Some obstacles must be always avoided, and the battery must not reach a low state, and from time to time, it should be fully charged. Omega 3 solved this problem in around 2 minutes on a MacBook machine. Let me show you how the simulation looked like. I hope you are seeing it moving now. This is part of the simulation. Now pickup 2 is done. Okay. Now to the last part of the talk. We discuss formal deployments of the controllers designed throughout the talk. Let me introduce formal deployments with some questions and answers. Question one. What are formal deployments? They are deployments that have well-defined execute and memory structure, known time-space complexities, and can be automatically generated. Question two, what are the types of deployments? First is control software on a stack, where the controller is a layer on top of a software stack. The stack can be, for example, a real-time operating system. The hardware here, the sensors are the actuators. Second type is the bare metal control software, whereas the software interacts directly with the hardware. They are much easier to reason about their correctness. In hardware implementation, the control software is translated to hardware circuits. Last question, why formal deployments? They are more predictable and can respect real-time constraints. They can be auto-generated and hence no human-related development faults may occur. Consequently, they can preserve the formality and guarantees obtained from symbolic control if they are used for symbolic control. We generally have two types of controllers to deploy. Static controllers or static symbolic controllers here have fixed control law for each state. The control law is a map C that assigns to each state a fixed set of admissible inputs. They are usually a result of synthesis of simple specification such as reachability or safety, and as a result of using state-of-the-art tools. Dynamic symbolic controllers have control law that depend on the state history. The control law here is a system, C, that have states and transitions. They are a result of a synthesis of complex specification. Currently, only Omega Threads can natively generate such controllers. Next, we discuss formally different possible implementations of those controllers. We start with lookup tables. Lookup tables are a simple way to deploy static controllers. One lookup table is used to represent one static symbolic controller. A row in a lookup table is dedicated to one state and its set of admissible inputs. In practice, no column is needed for the states since all states are represented unordered. Lookup tables are highly predictable in terms of space and time complexity. The space complexity is O size of X times times size of U, since we may need to store all inputs and for all states. Time complexity is O1, since retrieving a control input for one state is done directly in one step. The downside of lookup tables is that they are large in size, have empty slots, and if implemented in software, would require a verified compiler. An example software implementation is shown below. A computer receives the sampled state from an analog to digital converter, identifies its index, and uses the index to access the lookup table in the memory to retrieve the control inputs. Second implementation is using binary decision diagrams. They solve the space complexity problem of lookup tables. The control law is represented with a set of state input pairs and encoded as reduced ordered BDD. They are binary trees with log2 size of X plus log2 size of U levels. This comes directly from the binary coded decimal encoding of the states and inputs. For example, if we have 16 states, we need only 4 bits to encode them. The tree starts with an initial node and branches to either true or false at each node. The control law is encoded in those branches, in those paths that lead to the terminal node true. Reduced order BDD implementations are less predictable in space since they depend on the width of the tree, which in turn depends on the ordering of variables that is mostly done heuristically. It's, however, much more space efficient than lookup tables. Time complexity is more expensive as one needs to decode the state by traversing the first few levels and land on a subtree in the graph that represents all admissible inputs. The subtree needs to be explored further to extract all admissible inputs. The downside of BDDs is that they require longer time to access compared to lookup tables and more software layers to represent them. An example software implementation is shown below. A computer receives the sampled state from the analog to digital converter and identifies its index, starts exploring the BDD graph to reach a subtree, then it starts exploring the subtree to extract the inputs. Boolean functions are meant for hardware deployments, although can be also used for software too. The control law is first determinized, meaning that there is at most one admissible control input for each state. The control law is then represented by some Boolean functions. The number of Boolean function is log2 size of U. What happens here is that if a Boolean function regenerates a true or 1, this indicates that the corresponding bit of the input is to be set to 1. The Boolean functions together make combinational circuit as shown in the figure. The input is BCD coded index of the state and the output is the BCD coded index of the control input, which is the result of the concatenation of the outputs of the Boolean function. The content of each Boolean function is inferred from the control law, the BDD, or the lookup table. Boolean functions are faster when deployed as hardware circuits. Controllers are then hardware maps that take nanoseconds to process a request. The downside here is the long time to prepare the circuit and infer the functions from either BDDs or lookup tables or directly from the control law. Yet, this is done offline. Here is an example implementation similar to the ones before, but with hardware implementing the controller, and there is no software in the middle. Dynamic controllers are extensions to static symbolic controllers. They have different states. They can be treated as multiple static controllers combined with some switching logic. If lookup tables are used, one lookup table is needed for each state of the controller, and a software switching logic needs to be implemented between them. If BDDs are used, the state of the controller can be augmented to the state of the system, which reduces the complexity of the switching logic. The same applies to Boolean function. However, if implemented as hardware, the switching logic becomes a routing logic. For example, using multiplexers, registers, and so on. This is how our final end-to-end approach looks like. It supports more practical specifications using LTL or DPAs. The design development phase is automated and scales with the computing resources, which give us a chance against the curse of dimensionality. The deployments are formal, predictable, and most importantly, automatically generated. Most of the approaches we discussed are implemented in our tool, Omega Threads, with the help of prefaces. When needed, extensions for stochastic systems or complex reachability analysis tasks can be integrated using Amitis and PERC. This takes us to the summary of the talk. We revised symbolic control as a promising formal method approach for automated synthesis of certifiable controllers. 3 issues were identified in symbolic control: the curse of dimensionality problem, poor supported specifications for current tools, and lack of formal deployments. We introduced parallel algorithms for construction of symbolic models and synthesizing their controllers. We showed that parallel algorithms, along with variable resources, allow controlling the time complexity and mitigating the effects of the curse of dimensionality. We introduced an extension to symbolic control to support omega regular, represented as LTL or DPS. We introduce examples of formal deployments of symbolic controller. In a summary, we introduce an end-to-end approach for symbolic control. I'd like to thank my co-authors. Without their collaborations and the time I had with them, this work wouldn't have been made possible. I also like to thank the funding agents who aided this work, either directly or via equipment donations. Finally, I'd like to thank you for making it to the end of the talk, and I'm happy to take any questions.
All right, thank you so much, Mahmoud, for such an interesting talk. So, okay, then if, let's see if there are questions for you. So, Anna, yeah, go ahead.
Let me unmute myself. Okay. Yes, thanks for this very interesting talk. I have actually many questions, but let me focus on like 1 or 2. So one question that I was asking myself was that you showed this immense speed up that p-phases allows you to do, and then you said that you were using this to actually compute controllers for an example of a car taking like a car autonomous driving maneuver. And there you just briefly said that you were able to do some sort of controller synthesis online. Now, yes. I was wondering what type of controller updates you're doing online, or what additional information from the, you're using from the online deployment, and how this fits into the synthesis part, like how you still make sure you reach the goal and all these type of things. So is it the particularity of this problem that allows you to do this, or maybe just 2 or 3 more sentences of that would help?
Yeah, so simply we have like a simulator that simulates the dynamics of the vehicle, and we connected it to like a very powerful computer in the cloud. Yeah, if we ignore the communication overhead, you can also model it in some time. Then somehow the simulation itself it detects the environment and models other cars as obstacles, and then sends all this information to the cloud. The cloud is just doing the symbolic control problem. So it receives information like what is the dimension of the state space, where are the obstacles, what is the dynamics we are using for this car, and what is the time needed to solve the problem, then utilizes all available resources to solve the problem within the sampling time that we are working with.
But this is then only for safety control, or is this?
No, here it was reachability. So we have a moving window, like like a model predictive moving window.
I see. Okay.
And we designed the control, the next like steps to be applied to the car within this window, and apply them. Then repeat the window, keep moving the window, like model predictive control, but instead of doing like optimization, we solve with symbolic control.
I mean, I should add also that, first of all, it's reach and avoid, not reachability only, Mahmoud. Yes. And the other thing is, based on our I had some discussions with the company working on autonomous driving. They also said that, look, we always, because I think one of your question was which sort of guarantee you provide in this case. So after discussion with the autonomous driving or self-driving car companies, they said, look, even in their case, they have planning coming from a very complex optimization that happened in the computer of the car. They said, look, it may be the case there are scenarios that we may not be able to find a feasible plan that can navigate through this complex scenario. However, we always ensure you that we always have a safe plan. And what is that? Stop the car safely. So the same thing is here. In this simulation, we guarantee in the worst case scenario, those obstacles which are moving objects, they can stop immediately. And we ensure that we can actually stop the car safely. So that's the reason there is a, you may say there is a large distance between our car and the cars in front. That's because we take into account what if the car in front immediately stop. We need to be able, if we cannot maneuver, we need to be able to safely stop without colliding with the other car. So that's one thing that I just wanted to.
So it's partially from the particularities of this example that you have this kind of
Exactly.
default safety maneuver that you be able to enable in every
yes case. In general, you need to, yeah, you cannot have a generic solution in this case, you know, but this particular application, yeah, we were able to use that to our advantage. Yeah.
Okay, do I have time for one more question?
Yeah, for sure.
Okay, so this is related to the last part of your talk, where you showed this interconnection of P phases with some solver for parity games.
Yeah.
So this is maybe also a question for more details on a sentence that you just squeezed in, right? So at some point you said, oh, there is this complex algorithm that combines the system and the specification somehow in a way that this becomes efficient. Can you maybe spend 2-3 more sentences explaining this in a bit more detail? What exactly is the feature of this algorithm that goes beyond just taking the product?
It's a product like, but you know, there is some mapping happening like of the specification. So mainly, you know, somehow the symbolic model, we start with some initial region in the symbolic model, and also the parity automata. The parity automata has an initial state. So you can you know, construct this product step by step by exploring them. And this product is constructed in somehow special way to be a game. So that, like, you know, one step is like, you know, what a controller can do if he can apply all inputs. So the controller had the chance of applying all possible inputs. So this give us the edges that the controller can work with. Then you land up at some new states. Then at those new states, the system should respond. You explore the system. What are the possible branches the system can take? And you keep exploring. This becomes a game. For one step, the controller can play. For one step, the system resolves the non-determinism and picks one like option.
But you're not integrating this with the synthesis, right? So you're first constructing the entire game,
yes,
and then you solve it. So
yeah, we just use an off-the-shelf solver for now.
Okay, so what solver are you using for the?
Yeah, we use the solver from a tool called Strix. It's based on strategy iteration solving of the game, the parity game.
Okay. But this is enumerative over the game graph. Yeah. Okay. I can look this up.
Yeah, but just we parallelized it and implemented it in parallel in PFS. That's it. But it's off the shelf. It's not new. The new thing here is just the algorithm for constructing the game.
I see. Okay. Do you have this preprint online?
Yeah. The preprint. No, it's not online. But maybe once we submit the violent version to HSCC, I can try to make it available online.
I mean, I would suggest you just send via email to Anand. Yes. That would be totally fine.
If all the co-authors are comfortable with it, then I would like to have a look, because we're working on similar problems. So
all co-authors are here.
What? Okay.
All co-authors are here.
But you're feel free to discuss this offline, right? But I would be happy to have a look, right?
I'll send it to you by email.
Okay, thanks. So these are the urgent questions I have. So I leave, give the floor to other people that might have questions.
Okay, thanks, Anne. All right, any further questions? No. it seems there are no. Oh, okay. Let me see. Jamie Wang has indeed a question. Jamie, could you please? I mean, if feel free if you can also ask your question in person if you like. So I mean, okay.
Okay.
Let me.
Okay.
Jamie.
Yes.
Okay. So you
so
may.
Thanks for the interesting talk. So my question is you mentioned the sparsity of abstraction, right? So I don't really get what you mean. So I guess what it means that the graph of the abstraction is very sparse. Is that? So my question is how it is connected to the geometric property of the original system. I mean, when you have a sparse abstraction, what we can see about the system, or what kind of system will give you a sparse abstraction?
So actually here the sparsity is on the system itself, the dynamics of the system. So when you have like a discrete time system, you have like updated states at the left, and you have like equations at the right. And those equations have like states from the system. So if you take the first updated state, who of the other states are affecting it, we build this graph. This is the graph that we reason about sparsity.
Okay, so it's not about the sparsity of the abstraction.
Yeah, here is the sparsity of the
dynamics. Okay, I see.
Yeah,
thanks.
But it propagates also to the sparsity of the symbolic model.
I mean, one question I can ask on top of that. I mean, this sparsity of the dynamic, does it imply a sparsity of the abstraction, or does it allow for more, I guess it allows for more condensed representation of abstraction based on this reordering in BDD, correct, Mahmoud? Is that, can we claim that or no?
It's
of course
hard.
not scientific, not too formally, but heuristically based on experiment, is that happening?
Maybe, yeah.
I mean, one thing I do remember that, for example, in the case of traffic network you mentioned, so the serial connection of all these junctions. So you are utilizing the sparsity of the dynamic a lot, but also the size of the BDD is dramatically very low given the dimension of the overall network. So it seems that BDD is actually enjoying somehow the sparsity in the dynamic to its advantage and being able to have a very small BDD. So this is happening, but the question is, are they formally related? You know, that I don't know.
So there is like, now I don't know if there is a formal way to reason about this, but okay, let me say one thing. If you look at, like, you build a simple chart, the size of the BDD and how many set elements is it inside it. So if there are no elements, so the BDD becomes the 0 BDD. If it's all elements, the BDD becomes the 1 BDD. In the middle, the size of the BDD increases. So it's like a bell-like curve. The size of BDD compared to the sets you are storing in the elements you are storing in the set represented by the BDD. So where is your sparsity? Because if the graph is going to be fully interconnected, also the size of the BDD will start falling. So you can't say like it's like a linear curve where, like, you know, if you go to become more sparse, the size of BDD becomes less. Yeah, so it's complex. But yeah, if you are going to be much sparse, so yeah, going to no transitions, so the BDD will become very small. Yeah.
All right. So any other questions?
Sorry, just one follow-up question. Like when you define the sparsity of this discrete time control system, you define it to be 1 over the density of the graph, right, Mahmoud?
Yeah,
Is it
the density of the graph constructed from the interconnection between updated states and states. Yes.
So what is the density of the graph? How do you define that?
So I would say that the most dense graph, it's fully connected. All the states affect all updated states. All inputs affect all updated states. So you have fully interconnected directed graph. Directed towards updated states. Yeah. So this is like, you know, it's useless to use the sparsity here.
Mm-hmm.
No sparsity.
See, thanks.
All right. Any other questions? Okay, so if not, Majid, do you like to add anything before we wrap up, or